Right, recording started. So get to another Friday. So this Zoe experiment that I told you guys about earlier this week, where remember he was able to accurately calculate the speed of light back in 1849 using a toothed wheel in a mirror. That's going to be today's puzzle. Once you guys see the story, and then set guys up, let's show you. Let me have you do this. Next week, we're gonna take the whole week to do SAT prep, specifically on the math section, right? Because that's the part I actually help you guys out with. Okay, so take a look at this. What we got going on here? So the story is this guy's trying to figure out the speed of light, and here's how he did it. Oh, let me bring in with the picture on it. So he has some light source representing with a candle that's sending out light rays in all directions. There might be a ray of light that, say, goes between the gaps in his teeth. I'll call that a window. So a window between the teeth reflects off this mirror that might be several kilometers in the distance, maybe like 3, 4, 5 kilometers back. So it reflects off, comes back, and then this guy sees the reflection. Here's like an eyeball to represent an observer, observes the reflection of the candle in the mirror. Okay, so that's all fine and good. Okay. Now, the fact that light has a finite speed means that the scenario might be a little bit different if he gives this wheel a spin. Here's why. If this wheel is spinning fast enough, let's go back to the journey of, say, some photon going in this straight line. Right, so some of these photons are just going to hit the teeth and never go through in the first place, and some are going to go through the windows and bounce off the mirror, come back. And if this wheel is spinning fast enough, it might be the case that these teeth are now covering the windows that are adjacent to them. If it just turns just a few degrees, wouldn't that be the case? Okay. And then those light rays will never make it back to the observer, back to this eyeball. So what would the observer see? Well, the observer would no longer see the reflection of the candle in this mirror at that point if you speed it up to just the right speed. What would it look like speeding up to that speed? So if it starts from rest, this guy sees the reflection, all fine and good. Then you start speeding up, spinning this thing, give it maybe some angular acceleration, maybe. Right? So it goes. The reflection, well, it would look like there was a door that was closing on that reflection. And then, of course, once that door is completely closed and the reflection is completely blocked, that's exactly the angular velocity you want that you could use to solve the rest of this problem. And so what kinds of information would you have to figure this out? You might have to know something like maybe the distance to the mirror, which I gave you right here. Maybe you have to know the possibly the size of the wheel. Maybe that's helpful, possibly. Maybe the number of teeth on the wheel. Those could be good numbers to know. And also, of course, the angular velocity to calculate the speed of light. Now, I'm going to have you guys solve this backwards because you guys know what the speed of light is because we're all from the future now. You guys know what that number is. It's 3 times 10 to the 8 meters per second. Right, so I'm giving that to you. And I'm saying, what if you were to hop in a time machine, go back to 1849 and talk to this guy, say, hey, I can tell you how fast you have to spin this wheel. Suppose it has these particular properties. That's what you're trying to solve. Of course, he measured the spin rate, angular velocity, and calculated speed of light based on that. Right, so one way you can get there is I gave you guys some guiding questions on the right side of the page. If you answer these questions one by one, you'll get to it. Actually, there's at least a couple of ways you can get to the answer. And you know what else too? I'll tell you guys maybe a sort of a weird hint that may or may not be helpful, but maybe out of these 4 numbers that I gave you, one of these actually technically cancels out and you don't necessarily need it. Although, working through different paths, like different equations, it might be helpful to have it. You could apply it, but one of these numbers is actually unnecessary to have. The answer would be the same even if you change that number because it cancels out. So give you guys a hint, say on the first one, right? Get you guys started. So what distance did the light travel to the mirror and back? This could be like the first question on the helpful path that leads you to the answer. So one of the numbers I gave you was the distance to the mirror in kilometers. My paper says 3 kilometers. Everybody has a different paper, so you guys probably have a different distance to me. But if the distance from here to here is 3 kilometers, then how far did the light travel there and back? What would you guys say? If from here to here is 3, and light goes there and back. Isn't that like 6 kilometers? Right? Okay. And then one more thing, if that's kilometers, and you're doing some equation, it's probably good to have all your numbers in base SI units, like meters. So if my distance to the mirror is 3 kilometers, then the distance there and back is 6 kilometers, but that would be 6,000 meters, right? So I would write 6,000 in this box, right? And then you can go on down and figure it out. Okay, right, guess that? Right, so actually everything you need to solve this is all kinematic motion. Now some of it's linear kinematic motion, like maybe distance equals speed times time. Some of it's rotational kinematic, right? Because there's a rotating wheel. Do you guys remember some equations? Oh, do you guys see that poster over there on the wall? With a circle on it, it says x equals theta times r, v equals omega times r. Right? You guys remember doing that back in December? That might be a pretty helpful poster up there too. So here's the way we do this is, I mean, I'm really tempted right now to just like guide you guys through step by step and show you how to solve this, but today's gonna be more of a independent, working, creative thinking type day. So if you want to work on this by yourself, or if you want to work on this with your friends, team up with some people, go ahead. And you guys got the class period to figure out how fast was this guy spinning this wheel, and just turn this into the grade tray by the end of the class.